So thanks everyone for joining us tonight. Bienvenue tout le monde. We're very proud tonight to have Yala and Tatsuya from Korg who are going to do a presentation/conference and also a Q&A on the topic of innovation in electronic music instruments. Thank you.
Thanks, Victorian. Yeah, I'm Tats. We're from Korg. We're from the Berlin team. I'm Chief Innovation Officer, and Ile here. You might have seen the Phase 8 that we released actually at NAMM in January. It's a lead software engineer. And thank you so much for joining us tonight. I know some of you have come from afar, so thank you even more for that. Thank you, smem, for having us. And we're in a very special place here. Although, we've got some new stuff to show. We're, surrounded by beautiful synths from, some of them nearly 100 years ago. And so we thought we'd kind of like weave into the narrative of the stuff that we're explaining, some of the references from the history of synthesizers, specifically Korg synthesizers, to kind of navigate the story of how we got to Phase 8. So, okay, Korg, 1963. Thank you. That was the sound of the Doncamatic. The version you see here is probably the first one, and it comprised of a mechanical brain and an analog soul. And what we mean by that is that this version in particular had kind of a rotating kind of mechanism that would act as a sequencer, and that's the mechanical brain controlling the analog soul, which is actually tube circuits in their resonant filters making the sound. See here, that's the mechanical part on the left. And two people were involved in the development. Tsutomu Kato and Tadashi Osanai. And they met in Tokyo. And Osanai was an accordion player, and Kato at the time was managing and operating, I think 5 or 6 nightclubs in a kind of in a part of Tokyo, which was I don't know, kind of less controlled than the Tokyo that you might know now, like post-war. And they met because at nightclubs you need music. And Osanai was an accordion player who would entertain the guests. And he was very frustrated with drummers because some of them were unreliable, they wouldn't turn up, or even if they did turn up, they wouldn't play very well. And he had an idea to solve that problem by having a machine play the drums for him. And Osanai, although he was an accordion player, he also had a background in engineering, and believing in him, Kato, who had the money, invested in the project to make Doncamatic happen. Actually, I never met Osanai. I've been at Korg since 2006, late 2006, so coming up to 20 years now. But I never had the pleasure of meeting Osanai, but I did have the pleasure of working with Kato. He was chairman at the time, and his son, as president, was running the company when I joined. And for a few years, we were working in the same building, and he loved smoking, so we would hang out in the smoking area. I do have fond memories of him, although we didn't really, because I was just kind of fresh in the company, and I didn't have so many interactions with him outside of the smoking area. But he was always a very kind of kind and a funny gentleman. And in his last days, he he sent an email out to the whole company. He was like, yeah, diagnosed with cancer, don't have long to go. And he would send these emails out every couple of days until he actually passed away, titled 老人のたわごと, which means the ponderings or the ramblings of an old man. And he would just say very random stuff like, look after yourselves. Or he would say the word arigato, which is thank you in Japanese, comes from Buddhism, and it literally means hard to exist. So basically means don't take things for granted, means like be thankful for them. And he would just like kind of leave these kind of little paragraphs, and then he passed away in 2011. So once these two had completed the Doncamatic, they wanted it to be a commercial product, and a very different kind of commercial product compared to these, because it was actually a very kind of business to business. It was a B2B product. The price of the Doncamatic, I found out yesterday, was 280,000 yen, which converts after adjusting for inflation to about like 15 grand or something in euros or thereabouts. So quite an expensive machine, and really intended for other businesses to purchase it rather than musicians. And to release a product, they need a company. So they formed a company called, it's a mouthful, Keio Gijutsu Kenkyujo. That's the top one. And it literally means Keio, which is comes from the fact that they were near the Keio line in Tokyo. And Gijutsu, which means technology. Kenkyujo is R&D lab or like research center. And the company continued to operate under that name for quite a long time. But during the course of releasing more products, actually namely this combo organ, which came afterwards, they kind of merged the KO, which in fact are the two initials, K for Kato and O for Osanai. And they kind of combined it with the French word for organ, org. So that's Korg with a UE on the end. I think they later realized that the French connection was quite random, and then they kind of dropped the UE and just shortened it to Korg. But that kind of Korg kind of became to be that name through these two other identities. So they kept developing more products. I don't really know if the Doncamatic was a big success, but I do suspect that from the founding of this company in '63, for about like 10 years, I don't think any of them really took off. But correct me if I'm wrong, because I don't really know for sure. Commercially, there are famous instruments, Doncamatic's famous legendary instruments, but I don't think many of them made that much money. But they kept going. And the Korg 700, that's quite famous. We did a reissue of that 2 years ago, I think. And also the PS300 was during this kind of time, also reissued recently. Last year? Year before? Thereabouts. So the story continues to 1978. So that was the sound of the MS-20, probably one of the most famous of the vintage Korg synthesizers. And this was at the heart of the second generation of Korg synthesizers. I think this is a real poster. So this was it was a turning point for the company, really, because this is when synthesizers became more kind of like more of a commercial, like a businessly kind of profitable business. And if you think about the country Japan at the time, kind of rising from the dust of the war and becoming a real kind of manufacturing powerhouse of the world. And that combined with the very, very cheap yen at the time, I think it was something like 350 yen to the dollar, which is half of what it is now. And the yen's pretty cheap now, but it was even half of that at the time. And so that meant that they could really exploit overseas markets, and there was a lot of manufacturing, not just in synthesizers with cars and all these other big industries that really accelerated the production, the manufacturing of these instruments. At this stage, I'm going to keep using the brain-soul analogy here. So the instruments was at the peak of this kind of analog brain, analog soul era where we had CV connectivity. MS-20 is a semi-modular synth, meaning you can patch into almost all of the parameters, not all actually, about 80% of the parameters. And so you had analog voltage control over analog circuitry making the sound. So remember this photo of Kato and Osanai? I made it out as if that was when they met, but this is kind of about 10 years after that they formed the company. And there was, at this point, a third person, Fumio Mieda. And he had worked at Yamaha for a bit as well. And he was, or actually multiple brands. And he was a real inventor. He is a real inventor. Actually, to this day, he comes into the office. We've met him. And he's always, when you go and see him, he's always got this new thing that he's tinkering with. And so a real inventor mind that kind of most notably made the Univibe, the pedal, Jimi Hendrix, and the MS-20 filter circuit, which I'm about to show you, and also, oh yeah, more recently he invented like a new tube technology made with VFD display technology. So he continues to invent to this day, and at the time this is probably one of the most for me, the most kind of iconic inventions that he worked on, which is the filter. And I don't know how kind of schematic literate everybody is in the room, but it's a really funny filter. It uses, if you look at, I don't know if you can see, yeah, these two where my cursor is. These two transistors, they basically operate as kind of variable voltage controlled resistors. And when I first looked at it, when I first joined Korg and I was going through all the schematics to kind of try and learn how to design analog synths, I got really stuck on this because I couldn't really figure out what the operating region was of the transistors. And it's working in a very kind of weird part of the operating range. And so his thing really was to kind of, you could say like, not abuse components, but like use components in unintended ways. And I remember this was when I was working on the Monotron, which was the first kind of analog synth project that I worked on at Korg. I showed him the first circuit, and he said, "Yeah, Takahashi, your circuit works perfectly well, but it's a textbook circuit, and there's nothing musical about the design." And that's when it hit me that circuits shouldn't just operate and work according to design. They need that special something that only the maths doesn't give you of the circuit, that only those components and the silicons and the electrons and the holes and all that kind of doing their thing should be expressed in the sound. And this is a very kind of iconic design that really kind of makes that happen. Oh, my friend's not here. This was, I have a friend called Flavia, you might know her. And I was gonna point her out because they implemented this schematic. By the way, this schematic is a modern version, and the old version just makes that transistor bit that I just pointed out into a kind of like a black box. And the reason is Korg actually made what they call the chip, the Korg 35 at the time, and this contained those two transistors plus a bunch of other stuff around it. Maybe the FET around it was in there as well. And it's not really a chip, it's just a little circuit board that's kind of dipped in epoxy. Maybe to avoid other companies copying Korg, but it was also kind of part of kind of making efficient and streamlining production by having a module that you can use in multiple instruments. And I wanted to point out my friend Flavia because she has the schematic tattooed on her arm, and I was going to embarrass her for that geekiness. She'll come shortly though. Yeah, anything to say about Mieda? No, I think that's good. So, do we fast forward? Yeah, fast forward to 1988. That was the sound of the M1. So if we kind of think back to the previous kind of like 10 years before this, the sounds were designed by the electrical engineer, and they tell me that that engineer would kind of do the panel layout, they would design all the features, or select the feature set, and then maybe there's a mechanical engineer that does the case and implement the keyboard, and maybe the electrical engineer they write the manual, and so and they do the packaging together. So probably only like 3 or 4 people worked on the MS-20. Actually, that's an assumption, but they tell me that very few people worked on it. So this was designed with like very few minds kind of involved. And as business grew, and as business became more global, and as Korg became more of a kind of corporation than a research lab, it kind of started to divide the different disciplines into different teams. And the M1 really is a champion of kind of sound design. And at this time we had a dedicated team doing sound design, and the electrical team doing the electrical implementation, software team, and the manual was a separate team, and everything was different teams kind of collaborating with each other to make the instrument. So it was a very kind of different way of developing products. And this is the era of all digital brain and digital soul. And also enabled by kind of pretty kind of new technology with a cheap memory that's accessible even at kind of synthesizer level prices. And this culminated, actually, Korg had a really bad time from late 80s and dwindling business into the 80s, and got beaten the hell out of by the DX7 as well, which was selling really well. That came out in 82, I think. And actually, Kato, who used to own a majority of the company, needed cash, actually, from Yamaha, to prop up the business, and that continued until his share was like down to like 15% or something. So it was a time when Korg was actually getting bigger as a company, but also becoming less and less profitable, and kind of heading into more money problems. The M1 did really well and pretty much saved the company. I think we can thank the existence of Korg, the fact that it exists, to this product. This is a picture of Kato with, I believe they were named the MIDI Patch Boys. And that was coined by our German distributor, Meyer. And it kind of really illustrates how the company had changed from a bunch of people who just wanted to make instruments, and they kind of put it out, and then there was like manufacturing capabilities, and that kind of got merged into how we make instruments. And then it became a global business, and we have distributors, and we have subsidiaries, and people from abroad, like you can see in this picture, like racially profile that is like we had like Americans and Germans and all these other people making sounds for the hardware that the Japanese team was making, and it was a real success story of that collaboration. And after this, obviously, we have more DSP power. There's analog modeling era coming in the kind of 90s into the 2000s. And so the digital brain, digital soul era continued for some time. And actually, the M1 marks the very first workstation, the instrument that can become, you know, strings and pads and any instrument you want. That lives on to this day. So the modern day version of that in Korg is the Kronos. But really, the whole idea of the workstation originated with the M1. So there's a lot, but I'm going to jump 88, 98, 2008, nearly 3 decades to 2017. That was the sound of the monologue. I forgot why we picked the monologue over the mini-log, but maybe they didn't have the mini-log? Anyway, monologue. At the height of this kind of era of digital brain, so we had clever digital electronics controlling analog circuitry. And this, and I can talk about this a lot because this is really during my time at Korg and in Tokyo. And it really came about because, mainly because of ARM processors. You hear of ARM processors everywhere, but there's computing power everywhere. And ARM core processors really offered a way of having loads of processing power for not very much money, because they ended up in every kind of device that you can think of. And so we put that together with nice sounding analog circuits. And that started with, what was the first one? That started with maybe the Monotribe. Maybe you don't know much about it. It wasn't a massive hit, but it was a good synth. And then the Volca series, Minlog, Monologue, all those employed, or most of those employed, ARM processors combined with analog technology, analog sound technology. And I think I've got a, yeah. So this is, sorry, I'm jumping products, but this is actually for the Minilog. And you can see, you can't really see, but there's quite a lot of synthesis going on. I think in the Minilog we had like 30 knobs on the front panel. And we tried to make it one-to-one with the panel, so that was all the parameters that were accessible. But under the hood, there's a whole lot of maths going on, which is calibration of the analog circuits. I think it calibrates like 40-something parameters internally. So when you switch it on, you're waiting a couple of seconds for it to start up. It's actually measuring how the analog circuit's doing and configuring itself to be able to work with that so that it is in tune and that they're stable and all the parameter ranges are nice and the curves are good. And so it's doing all that maths inside. And this really enabled us to manufacture fairly complex analog synthesizers, again, without doing kind of hand selection and measuring components before populating PCBs and all these things that make analog production difficult, were circumvented by this clever kind of digital brain that we now had access to. So this really drove this, and actually culturally as well. There was a whole kind of, return to kind of more simpler instruments, things that didn't overwhelm you by having, 100 different sounds and, like infinite polyphony. It was a time when people were coming back to kind of basics, and they wanted to kind of be more in touch with how the synthesis was happening. So it was really a good time when the technology and the kind of cultural shifts kind of met. And these synths did really well. They still do pretty well. This is, I found this video a few months ago. This was around, I think, 2014 or 15, when I was working on the Minilog. And I thought it was interesting to show, because previously I talked about how the electrical engineer had to do the sound design, because you couldn't separate that and get another different team to do it, because the circuit really defines the sound. And this is a video of me at a very late stage in development. We call it P2, which is pretty much the final prototype, and you shouldn't really be changing stuff. But I had to tweak some parameters, and this video kind of illustrates when you have like a polyphonic analog synth, you have to change quite a lot to change a couple of tiny details in the sound. So basically we're back to kind of, fewer minds creating the instrument era. So maybe I do that. I had short hair. Of course, you can see like surface mount components. That's really helped a lot in realizing fairly complicated circuits happening on one board. And so yeah, so it's that repeated many times until we get to a product that we're happy with. And it's kind of hard, because you have to do it. You can't give it to somebody else to kind of design the sound. The electrical engineer has to do that. So it's hard, but it's also very fulfilling and a lot of fun. I think, is that the last one in this? And then so the monologue came out, and I was having a great time, but I also decided to take a break from the company, and I left Korg actually in 2017. How do I get the next slide? I took a break from Korg between 2017 and actually moved to Germany to pursue a different job. And I remained consultant for Korg, so we would keep a kind of a light working relationship continuing until 2020, when Korg decided that they want to start something in Germany, and I got a phone call to do it. So that was the kind of 3-year kind of break from Korg, and now we're back. And this is what we made. So we decided to do it in Berlin. I was living in Cologne at the time, but I moved to Berlin, and we built, these are just like kind of mood shots from our working space. This is where we work. We made a new office, which has a studio and a nice workshop where we can prototype. We have a CNC milling machine, which I always dreamed of having. So that's a dream come true. And also we have a lovely team that we assembled. And of course, it's great when you have trust and investment to create a new space, a new workshop, and assemble a new team. But we also needed to figure out what we're going to do, because we weren't really told what to do. It was just like, yeah, start some. This is coming from actually Seiki Kato, the son of Tsutomu Kato, who founded the company. He sadly passed away last year. So 5 years ago, 5.5 years ago, he gave us the opportunity to start something new with pretty much complete autonomy. So we had to figure out what to work on, and it would have been quite nice to do, maybe another, subtractive analog synth or some hybrid synth, but we kind of realized that there are loads of really good synths out there already, and the market is actually quite saturated. So even from like a business perspective, how can we do something that's meaningful for the industry, also give us purpose, and not become just another synth in a whole, big sea of really good synths. So we came up with a new technology to make sound. We decided to go beyond electronics as a means to make sound, and to go into acoustic synthesis, a mechanical means of making sound, and combining all of that with sensibilities of other synths that we've been working on. So and the first product to come out from that exploration, fast forward to this year, 2026.
That's us. Yeah, I'll take it from here. Yes, so this is our new synth. It's called the Phase 8. It's the first concrete commercial product to come from a period of exploration into, new interesting kinds of making sounds. It's sort of, in a way, if we look at, we had this kind of way back in the day, a mechanical means of controlling an electronic sound, and they had various generations of electronic, both analog and digital sounds. There's almost like a reversal of the very beginning, where we now have an electronic means of controlling a mechanical based sound, I guess. We wanted to do something that feels quite alive in a way that's very, very familiar to anyone who's played a piano or a guitar or a flute or banged on a drum before. But also something that sits quite snugly into the world of the nerdy world of synths, of which smem is, to which smem is a monument. And although it's maybe not the first ever instrument to have electronic control over mechanical means, those instruments tend to be very big, very, very expensive, and quite rare. We have like self-playing pianos, like with which Aphex Twin makes music, and so on. Various experimental rare synths. But we thought it would also be cool to have a product that fits in with the world of available synthesizers that uses this idea of electronic control over physical means of sound. So the way that it makes sound is much like my faders. I've mixed myself out. Oh, sorry, my slides. This illustrates the brain, which is, I suppose, cool, but maybe unremarkable in a world full of products that have little cheap digital brains. Quite similar to the brain, which tunes, sequences, triggers, controls the circuits in an analog synth. But yeah, applying it to this mechanical means, which turns out to be quite difficult when between one thing and another. There's all sorts of questions to do with how do you, if you want a mechanical means that's controlled electronically, how do you do that? How do you bridge the gap between the thing that's mechanically moving and making sound and this brain digital control world? And yeah, I guess next one. Cool. And these are the resonators themselves. So this instrument has 8 of them, although different instruments could have any number of them. But in this instrument, it's got 8, I suppose, pitches, 8 voices, 8 pitch centers. And that can be set to an arbitrary scale within a certain range. So within the range of, I think, C3 to C4 for now. You can pick any combination of pitches, including non-standard micro-tuned pitches, and create a set of 8 pitches and sequence them, as demonstrated here, and make them vibrate to hear them make sound. This illustration over here on the right is kind of a graphical illustration of how a body like this makes sound. Things when they vibrate tend to produce the character of their sound, as many of you are probably familiar. Depends on all of these frequencies that stack up within them. So oftentimes guitar players will be familiar with harmonics, or the idea that actually any instrument that works with a string, which is clamped at both ends, will produce this predictable, in some ways predictable stack of harmonics that, but with different amounts of the different harmonics depending on the properties of the string. Our instrument, not a million miles off that, but also not exactly the same. It's not quite a string, it's a beam that's clamped at one end, maybe. I don't know if it's visible. And so based on the length, the width, the thickness, and also this circular hole that's sort of punched out of the middle of each of them, we get, bizarrely, we get different kinds of overtones, which seems kind of non-intuitive and would have been quite difficult to figure out without simulation. So these images are from the simulations that our colleague Lucas runs in order to figure out, okay, if I have a body of this length and this thickness made of this material with a hole punched out of it, what are the behaviors of its overtones? And using this technique, we've sort of sculpted a first example of a sound that we quite like. Although this logic can be taken in quite a number of directions, you can use these simulations to come up with a forked shape or cut out slats out of the side, or basically any sort of shape change that you make to the resonators can influence their overtones and therefore the character of the sound. And in this case, we've gone for bar with a hole punched through it. But stay tuned for more. Yeah, please. One of the challenges with making an instrument like this is how to drive it, so how to get the thing to move under electronic control. Many people, when they see this instrument, and they're music nerds, will think immediately of a Rhodes piano. They may also think of a kalimba first, but if they think of a Rhodes piano, they often imagine that this coil at the very end of the resonator is listening to the sound of the beam moving up and down. As a Rhodes piano does, it has these beams with a coil at the end, which is electromagnetically listening to the movement. Ours is kind of flipped around in that the one aim of this product that isn't, I guess, part of the design of something like a Rhodes piano is that we want to be able to trigger the resonators at precise time intervals, arbitrarily fast. And to do that, we came up with this electromagnetic driver. So these coils that sit under the resonators, instead of listening to the sound, they actually create their own magnetic field. And given that these resonators are made of ferromagnetic material, they will respond to the signal that's driven into the coils. Also kind of similar-ish to the principle of how a loudspeaker works, this idea of pumping current into a coil in order to get something to move through magnetism. And then in our case, the pickup, the thing that is a coil in the case of a Rhodes piano, in our case is this flat black surface underneath the resonators, which maybe isn't so, yeah, thanks. Which in this instrument works quite a lot like a condenser microphone. So the condenser microphone contains two, although much smaller, plates which move with respect to each other, and the capacitor that those two plates create as air moves one of the plates around creates an audio signal. We've done the same thing here but bigger, and there's 8 of them, I guess. And this combination, although it's quite sleek and we're quite happy with it now, it took quite a long time to arrive to. Turns out there's quite a number of ways you can quite a number of ways that you can pump a magnetic field into something metal, and arguably even more ways you can listen to its movements. And all of those things come with a huge array of trade-offs and cost implications and noise and signal considerations. But yeah, we've landed on this kind of core combination of this electromagnetic driver, this metal moving body, and this capacitive pickup. And this is the first product that collects that idea into a playable form. Hit it. Thank you. This is an illustration, I guess, of the process I described. So in this instrument, we're chucking pulses into the coil, and the pulses create this magnetic field somewhere around this yellow box, but also kind of extending out and decaying as magnetic fields do. And then this circled purple area is where the two surfaces moving relative to each other make the sound that we can hear. So that sounds like this. Let me change it. A few knobs are down. So this is the mechanism by which we can either strike them on a once-off basis or run these kind of controlled sequences. One cool factor that the digital brain part, one cool role that plays in this instrument as well, which is also, I guess, a research direction that has been a big part of our work on this instrument, is that as well as just striking the resonator once like this, we can also do the following. We can take what's happening at the pickup side, so the audio that's created on this, and the little computer in the box listens to this signal and then can keep providing energy through the coil back into the resonator in order to get it to sustain for as long as we want it to. So that sounds like this. That's tremolo, sorry. And so this is, yeah, another trait of this instrument. It can be heard in this sequence here. Oh, tempo's down here now. Yeah, that's another trait of this instrument, which I guess illustrates this idea of how the brain and the soul, in this case, what we're calling the metal resonators, interact. Yeah, so that's the instrument we've came up with. It is only the first of our creations to come out, but we're pretty excited about it. And yeah, thanks for listening. We can totally answer any questions about anything, really, if you have any. Yeah, thank you.